You'll probably be able to tell that I was slightly nervous in this interview, but what an incredible person and fascinating discussion. This is an interview with Stephen Wolfram. He's a computer scientist, mathematician, theoretical physicist, and the founder of Wolfram Research, the company behind Mathematica, Wolfram Alpha, Wolfram Language, and the Wolfram Physics Project. He was so generous with his time and even extended the amount of time he'd set aside for me. But even though this was the longest interview on the channel to date, of course, we'd only just touched on some of his ideas. And so I hope this inspires you to go and delve deeper into his work by reading some of his books. In particular, I can recommend his book on the Wolfram Physics Project and A New Kind of Science, both of which I've linked in the description. The Wolfram Physics Project is also very open source, and there's plenty of information on the project's website, which I've also linked. We talked about a lot, from his educational experience to cellular automata and complexity, to the Wolfram Physics Project and a handful of its striking discoveries, and much more. Enjoy. All right, so I want to talk about some of your ideas in a minute, like from cellular automata to the Wolfram Physics Project. But just to start with, because these interviews are aimed at a student audience wanting to, I kind of wanted to look at your own student days. So you took a quite unconventional path and were clearly very, very driven from a young age. Tell us what shaped your decisions. Sorry, that was your decisions.
Well, okay. So I grew up in England in the 1960s, and that, which is outrageously long time ago for those around today. But in those days, the big thing was the space program and space and so on, and that was kind of the future was all tied up with space. I'm glad I didn't stay in the space business, because I would have been waiting for 50 years for something to happen.
Yeah, it's certainly taken a while. Yeah.
It's, I mean, it's sort of ironic that a lot of the physics I'm studying now has to do with the structure of space, but not in the same sense as the space program, I guess.
Very different.
So I got interested in, I followed every, in 1968-ish time frame, I sort of followed every spacecraft launch and all those kinds of things. And I got kind of interested in, then I got interested in sort of how would you design spacecraft to do things and how does spacecraft work and so on. And that got me kind of backed into understanding things about physics. And so by the time I was, I guess, maybe 11, 12 years old, I was 11 years old probably, I was reading lots of physics textbooks and such like, and trying to understand physics. And I guess I sort of got interested in more and more foundational kinds of things. And I think one important sort of thing for me was there's a cover of a book about statistical physics, which is some kind of college textbook, that has this sequence of images that purport to show the second law of thermodynamics in action. And I got age 12 or so, I got really interested in that. And I was disappointed that the book kind of said, explains the sort of second law of thermodynamics and gives a totally lame explanation, which it kind of admits doesn't really explain how sort of complexity and randomness and so on actually arise in the world. So I got interested in that. Then I went to a fine little school in Oxford, England, which is was around lots of kids of academics, as I was, and my mother was a philosophy professor in Oxford, and the main thing I learned from that, I suppose, is that, well, at the time I said, if there's one thing I'll never do when I'm grown up, it's philosophy. And if you look at things I've been writing in recent times about things like, why does the universe exist and so on, I guess, 50 years later, turns out I wasn't quite right about that. But it was, it's kind of, so I went in the British system. I don't know to what extent you're dealing with a British audience, but I ended up, there's the whole sort of scholarship exams thing at age 12-ish or so. And I went off to Eton, which was sort of at the time, I don't know if it's still considered sort of a fine top, if not particularly science-oriented school. And I think I went there because I had sort of calculated had the largest scholarships, although it didn't really make that much difference. And but it was an interesting group of people anyway. I think we've all gone on to do, or most have gone on to do interesting things. But anyway, so when I went there, got a fine kind of classical education, with me mostly objecting that when will I ever use knowledge of Latin and Greek and history and all these kinds of things. It turns out almost everything that I learnt in school, I've turned out to use. I have a decent memory, so I remember all these, even these weird Latin irregular verbs, I think. Who can test me, but you know, it's ended up
for years.
It's you know, the big surprise has been that I actually use all that stuff, and it's like, you know, I'm having to name things, and I'm having to sort of think, oh, can I come up with a nice Greek rooted name for that thing? Often ends up not being Greek rooted in the end, but at least one tries that. But anyway, so I was went to sort of a fine top school, although most of what I was really interested in was stuff that I was doing kind of on the side, working on learning about physics. And I got really, at the time, particle physics was sort of a big thing. And I got sort of pulled into that. I guess when I was like 12 years old, I did this thing which you can find somewhere on the web, which is a little sort of summary of physics, sort of directory of physics and so on, which has a certain depressing resonance with things that I've done in subsequent years, because it's kind of collections of knowledge and facts about physics and so on. And it's kind of like, you know, that's what the kid who goes on and ends up building Wolfram Alpha does when they're 12 years old and so on. And when I found that document years later, I kind of, you know, I guess I found it before we actually had released Wolfram Alpha, but when we had Wolfram Alpha up and running, I was like, let me type in some numbers from this thing I wrote when I was 12 and see if we can actually compute them now. And yeah, we did well on that. But then I got interested in it was a time, mid-1970s was kind of the golden age of particle physics. It was at a time when, you know, most fields go through these kind of periods of when sort of nothing much is happening, and then there's usually some methodological advance, and then suddenly there's lots of low-hanging fruit to be picked and lots of exciting discoveries to be made. And that's kind of what happened with particle physics around 1973 or so, with kind of discoveries around quantum field theory being made. That quantum field theory had been invented actually in the late 1920s, and it sort of gradually moved forward things in quantum electrodynamics done in the 1940s and so on. But it kind of got stuck, and people didn't know if quantum field theory was going to be the way forward. And then in the very beginning of the 1970s, it's kind of a bunch of things happened that led to what's now the standard model of particle physics and so on. And that really got to, it became clear there was lots of exciting stuff to do. And so I was, I guess I ended up producing, I don't know, I seem to be fated to do expositional kinds of things. And I produced two kind of, you know, you can find them on the web now, typewritten sort of book-like things about particle physics, one about general particle physics, the other about weak interactions. And when I was like 13, 14 years old, actually, it's kind of funny because you know, there's some history of particle physics stuff, which I covered in one of those, where I was looking for that recently. And it's like, I searched for it on the web and I end up finding my own stuff from when I was like 13 years old. And I think I was thinking of putting some legend on it saying, look, I was 13 when I wrote this. I don't know if it, you know, I've no guarantees that this is the definitive history of particle physics.
Sounds like quite a surreal experience. Searching
yeah, a little bit amusing.
Yeah.
I mean, it's kind of a little bit depressing actually, because kind of, you know, particle physics had been such an energetic field in the mid-1970s. And then when I sort of went back and looked, so what happened with all this stuff? A lot of burnt out stuff, a lot of stuff where things have been really exciting and happening at that time. And this is very typical of lots of fields of science, that they have periods of great sort of advance and then kind of coasting periods that can last, well, as it did for the space program, kind of last most of a career time, so to speak. But I think, anyway, in my own sort of trajectory, I one of the things that was sort of big for me in the, well, two things happened in the kind of 1973, 1974 time frame. One was a thing called the J-psi particle was discovered in particle accelerators. And it was like, what is this? That was an unexpected particle. And everybody had to have a theory about it. And the 14-year-old me was one of those people. My theory, it's kind of I think it's the only time where I've actually had sort of a theory, which at least at the time was definitely not right. And I've sort of prided myself on whenever I've actually stuck my neck out to have an actual theory of what was going on in some situation. It's been, I've either not said anything or it's turned out to be a correct theory. But what that theory kind of posited the idea that electrons are not really point particles. In traditional quantum field theory, traditional particle physics, electrons are just zero-sized geometrical points, at least intrinsically so. They're kind of, they collect around them a cloud of virtual photons and other such things. But in their intrinsic nature, they're thought of as zero-sized point particles. And this kind of posited a kind of a situation in which electrons would have a size of like 10 to the minus 18 meters. Turns out not to be true. Ironically enough, in our current theory of physics, once again, electrons have non-zero size, although I think a rough estimate may be, not clear this is right, but a rough estimate of possible size is 10 to the minus 81 meters. So they flipped around the digits in the exponent and off by 60 orders of magnitude or something. But anyway, that was the first, that thing caused me to write my first kind of paper that I sent into a physics journal and got published and so on. I don't think it was a particularly good paper, but it's amusing when one's 15 years old to have all these little, in those days, people used to request physical preprints of papers, and I would get all these cards. I was at boarding school then, and all these cards would arrive at desks to, Dr. S. Wolfram, and it was very amusing for my co-student, so to speak.
Sure, yeah.
But I think, that then the other big thing that happened at that time was that I started using computers. And I think the school that I was at had a computer, which wasn't very common at the time. It had come through a rather circuitous route, actually, that had come from a teacher who was there, who I knew quite well, who had been a friend of Alan Turing's and had worked at the National Physical Laboratory, and somehow that had wound up with the school getting a thing called an Elliott 903 computer, which was the size of a large desk and programmed with paper tape, and was kind of it had 8,000 18-bit words of memory, kind of small by today's standards. But so anyway, I started programming that, and one of my goals was to reproduce the sort of second law of thermodynamics phenomenon that was shown on the cover of the book about statistical physics that I've been interested in. And I ended up writing these programs to do that, and it wasn't particularly easy to write physics simulation programs on a computer that's that primitive. And I ended up sort of simplifying the programs to the point where actually I ended up having a cellular automaton, a very simple program that I ended up studying years later. And through a somewhat technical detail, the program that I made at that time did nothing interesting. So I didn't manage to reproduce the second law of thermodynamics behavior, and I kind of put it aside. And but I did learn to program computers, and I wrote a bunch of kind of systems level code and things for the computer, paper tape loaders and other such exciting, not very modern kinds of things. But then I kind of gotten, well, let's see, I did what, in England, it always used to be a badge of honor to say, I left school at 16, so to speak, and I did, because and I mostly was doing, I mostly was sort of doing things on my own, doing physics and so on. I used to go and take the train and go to the physics seminars in Oxford and so on. I think that's a multiply edged sword, because I was a brash young fellow, and so I would show up at age 15, 16 or something at these physics seminars, and I would ask questions, and sometimes I would ask rather probing questions. And so I think that I kind of got, and the physics community is a pretty international community, and so people would come through and visit and so on, and they'd run into this brash teenager and such like, and so I think I got this reputation as a brash teenager, and because it's an international field that doesn't have much turnover, I think still, 45 years later or something, I think in some ways I still live down the sort of image of the brash, 15-year-old me asking awkward questions of people talking about random physics topics and so on. So it's amusing to be kind of early in those things, but it has some strange features. But anyway, then I went. Let's see. I guess the way the British system worked at that time, if you got a quote scholarship, which was largely honorific because the government paid for everything anyway, to Oxford or Cambridge, you could skip doing the standardized exam, A-level and things, and so that's what I did when I was 16, and I ended up going to work at this place called the Rutherford Lab, which is a physics research outfit in England, and doing theoretical particle physics. And I wrote a number of papers that got progressively better, I would say, at the time. And I also, they had a fine mainframe computer that was connected to this thing called the ARPANET. That subsequently became the internet, so to speak. And so I started being able to make use of, at that time I started using computers to do algebraic calculations, which was something that pretty much, other than the people who'd written systems to do that, nobody had the idea, it seems, that you could, because in doing physics, particularly particle physics, it ends up that there are these, really messy, complicated algebraic calculations to do. It's kind of remarkable that when you do them all, you seem to get the right answer, but it's difficult to actually do them. And people would pride themselves on being able to be the finest, doer of integrals in the land, so to speak. And it turned out I wasn't that keen on those things as a hand doer of integrals and such like, and I kind of learnt that one could use computers to do those things, and so started doing that. So that was then. Well, I went to, after the Rutherford Lab, I went to Oxford as an undergraduate. I didn't really. It was, I don't know what the system is these days, but in those days you didn't have to show up to lectures and things like that. You could just do what you wanted, and so long as you did the exams at the end of the first year or something, you could sort of do whatever. And the only thing that I did that was part of the sort of standard sequence, I think, was the experiments, which I kind of found interesting, and it's sort of an opportunity to play with, actually get one's hands on various physics kinds of things, and sort of useful intuition really to do that. But mostly I ended up getting using the computers of an experimental particle physics group that I guess helped with some data analysis for in return for using their computers and their connection to the ARPANET and so on. And I was off writing physics papers, and at that time I got interested in the connection between cosmology and particle physics, which was then not a thing people talked about. And one of the big things I'd been interested in is how come there's more matter in the universe, or at least around us in the universe, than antimatter. And that was kind of one of the things. And how come the universe can go from this, and again, it's kind of a thermodynamics type story. How can the universe go from this kind of initial condition of the Big Bang, where it's this big hot gas of expanding stuff, to something where there's all this structure and galaxies and things formed by gravity and so on in the universe? And I was very interested in that, and interested in whether the second law of thermodynamics applied to gravity and things like this. That was, but what I did for, wasn't quite my day job yet, but what I ended up doing, I wrote papers about, particle physics and QCD and things, and then some papers about the relationship between things that happen in the early universe and particle physics. It's, one of the features of being in a field when it's in sort of its rapid expansion kind of low-hanging fruit phase, is that you can be a kid and you can write papers and people still read those things decades later, because it was you ended up being the first person to pick that particular piece of low-hanging fruit. Probably somebody else would have come along within a few years and done it, but because you were sort of first in the area, so to speak,
and you get to see yourself coming up on Google several years later.
Yeah, right. Well, it's the but anyway, so I mean, to finish you asked about, so the education trajectory, I suppose I left Oxford after maybe a year and a half, and I had spent some time in the US at a national lab in the US over the summer, and ended up going to graduate school in the US at Caltech. And if I had put any more effort into it and thought it would be, had any interest in being able to say it in the future, I could easily have gotten my PhD while I was still a teenager, but I didn't. And so I got my PhD when I was just turned 20. And then, well, I had various sort of job offers to sort of be a physicist, which have been my kind of goal for the last, since I was like 12 or so. That had been somebody said, what do you want to do when you're grown up? I'd say, be a physicist. And so when I was 20 or so, I guess I was a physicist, and I ended up staying at Caltech on the faculty there for a few years. And if things had worked out differently, I'd probably still be there today. And, I have many friends who were kind of typically a bit older than me, but in the same track as I was on, and they stayed, they were physics professors their whole lives, so to speak. And I could have done that. I didn't do that. I didn't do that basically because, well, I had worked on particle physics for a while, and then I got, I sort of was into using computational tools to do things, and kind of reached the edge of what the world had already built in terms of computational tools. So in late 1979, kind of said, well, if I really want to make the next stage of this, I got to do it myself. And so I ended up building this thing called SMP, symbolic manipulation program, which was kind of a predecessor of Mathematica and Wolfram Language. That was my first big software project. It was kind of released it in 1981. And I ended up starting my first company around that. Turns out, in those days, at least, doing the company thing and doing the professoring thing didn't mix terribly well. That kind of caused me to look elsewhere. And meanwhile, in the middle of all of that, I got interested in kind of what is sort of the most foundational thing you can build to make models in science. And I had kind of thought, oh, it must be particle physics and so on. But then I realized that sort of there are lots of things in physics and elsewhere where sort of complicated behavior happens, but what's the essence of the phenomenon, so to speak? And that got me into kind of studying simple programs, kind of building it up a little bit like how I built up the things in my first computer language. And so in 1981 or so, I started studying these things called cellular automata, which are kind of extremely minimal, simple rules, simple programs, where you just have a line of black and white cells and just say at each step, update the color of a cell according to the simple rule. The rules can be incredibly simple, and yet the behavior you get is very complicated, something that I was super surprised about. And it's kind of my all-time favorite science discovery. And it's sort of a thing that unlocks a lot of understanding how complexity occurs in nature. And I originally kind of started studying cellular automata and the intersection of studying self-gravitating gases and neural networks, which I had gotten interested in around 1980. And turns out cellular automata are uniquely unsuitable for studying either of those two things, but they are a great source of they're models for lots and lots of other kinds of things, and a great kind of source of intuition about sort of how things work. So anyway, that's you asked about my education trajectory, and I suppose I had the perhaps good fortune to get through the sort of traditional education track pretty quickly, and before I had kind of decided that it was too that I didn't like it. And I think there were two meta discoveries I suppose I made. One was you can learn stuff just by reading books. That's an important meta discovery. Maybe three meta discoveries. That's one. Another one is near any problem that's an exercise in a textbook is a problem nobody's ever solved before, and those are more fun. Also, kind of you look at what the textbook says and you say, I wonder about X, Y, Z. And I mean, because I sort of did wonder about XYZ, and then I'm like, can I figure this out? The fact that the textbook doesn't say, it's not an exercise in the textbook, doesn't mean you can't figure it out. Now, sometimes those things that I started thinking about back when I was a kid, I still don't know the answer. Many of them I have figured out in intervening years, including the second law of thermodynamics, as it turns out. But like sometimes these things that are, it's always, and sometimes it's the case that there'll be some foundational question, some question you think is an obvious question to ask. Turns out nobody's bothered to ask that. They stopped asking it because everybody said, oh, that must have been solved, or that's too difficult. And turns out often, and sort of it's been part of the story of my life at least, is you come back to these things, 100 years later, let's say, and you have completely different tools, quite different intuition. And turns out those foundational questions are not unassailable at that point. In fact, you can make huge progress with them, but people kind of avoided them because it's like, we know that's a foundational question, that must have been solved, or that must have been that's too hard, so to speak. And I suppose the third meta thing is, use the best tools and learn the tools well. And for me, obviously I've spent a long time building up our computational language, Wolfram Language and Mathematica and so on. And I'm a good user of those things. I use them all the time. I use them every day. And, the things I've discovered, there's no way I would have been able to discover them without that technology stack. And without, both for me, it's been very invigorating to kind of go back and forth between basic science and technology, because each one kind of informs the other. But it's still, in terms of people sort of studying physics and things like that, it's, learn the language we've built. It's because then you can, among other things, you have a tool that never existed before. And you can go back to things people studied, decades, centuries ago, and you've now got a new paradigm, a new technology, a new approach to cracking those things. And turns out they often crack. And turns out that you can make huge progress. But in order to do that, you have to be fluent in the language and the tool, because otherwise you're like, oh, I don't know, maybe I wonder about this, but it's too hard to write a program, and I'm never going to look at it. And for me, it's kind of like, I wonder about something, I write a piece of code, it takes me, if I'm lucky, just a few minutes, and then it's like, okay, I'm generating all kinds of stuff, and I know what's going on. And maybe it was a dumb idea, maybe it wasn't a dumb idea, but quickly, and you're kind of having sort of a huge help from your computer, so to speak, to kind of get you, it isn't just you, it's you and your computer. And that's a really powerful combination, so long as you know how to wrangle your computer well.
Is there any advice you would give your teenage self, just finishing that off, looking back, aside from trying a different rule earlier on, which I'm sure
to people today studying physics and things?
For people today, or looking back, advice you wish you could have given yourself back then? I know those are the things you learned. Is there anything that you've learned after that you wish you'd known then?
I don't know. I think I was perhaps, when I studied physics at the beginning, as it's turned out over the course of my life, I've learned lots of different fields, and knowing lots of fields is super useful. And I think I would have encouraged myself to protest less about learning things that seemed irrelevant at the time. I think also another thing is, one thing that's been a feature of at least my way of doing science is you really can understand stuff. Whenever you're floating at a level where it's like things are happening, but you can do this technically, but you kind of don't understand it down to the bedrock. Turns out you might think you'll never, will be really hard to understand because there's a whole bunch of technical detail there. But it turns out eventually you get to sort of a pattern where you can really actually drill down and understand down to sort of the bedrock. I'm not sure that I would have been able to do that when I was, actually, I think I did a lot better than I remembered myself doing, because when I read stuff I wrote when I was like 12, I actually understood it better than I thought I understood it, so to speak. But it was, I think in one of the things that's always important, something I think I happen to not have a sort of to find fairly easy, is the strategy of what you do is ultimately more important than the mechanics of how you do the things you do. So in other words, you can be a fantastic solver of all kinds of problems, and fantastic solver of physics problems, and then you just go work on completely the wrong problem. You get nowhere, or the results just aren't very interesting. And then all of that mechanical skill, so to speak, is completely wasted. So the kind of strategy of what should you study and kind of what approaches should you take, that's not something that they teach in school, so to speak. They teach kind of the track that's already been followed, so to speak, rather than if you're going to do something that hasn't been done before, how should you think about what to do? So kind of figuring out the right question. And I think I've interacted enough with kids today, so to speak. Somehow, lots of kids ask all kinds of interesting questions, but teachers probably tell them, oh, those are too difficult, or, oh, you'll learn about that if you go to physics graduate school or something like this. But it turns out, it's like, okay, maybe, but, you can still think about it even when you haven't gone to physics graduate school. And sometimes there are questions where, for me, I don't tend to be a textbook learner of things. I don't think I've read very many, textbooks as textbooks, so to speak, in my whole life. I tend to learn things when I have some project, something I'm trying to figure out. And then, it'll be something, and perhaps some abstruse area of mathematics or some other field or whatever it is. And then having defined that endpoint, having defined sort of what I'm trying to figure out, then I kind of learn the path that I need to be able to answer the question that I'm actually trying to figure out. And that's, for me at least, and, people's personalities differ. Some people, for me, if you say you're going to do a physics competition, I would say, no, I'm not. I'm going to run away. I'm not interested. No interest in that. And, if you'd say, you're going to, get a great, do this class very diligently and get a great grade, I'm like, okay, fine. I just not something I'm interested in. It's, I suppose, for me personally, and if I were to, I suppose it's a piece of egotism on my part at some level, that I like to think I'm doing something that is unique and wouldn't have just been done by a bunch of other people. And if I'm doing like the exercise in the book, it's like, I know this has been done by thousands of other people. It's like, why am I doing this? I'm doing this sort of to improve myself, but I can improve myself in ways that are sort of more unique, and that's more fun, so to speak, and more motivating. So I think this thing about sort of the strategy for what one does and what one chooses to study is really important. And I think, at any given time, there are things that then there are a couple of other issues, like at any given time, there are fields that are very active, very energetic. Everybody knows they're important. There are sort of key problems, and everybody's kind of marching towards those key problems. That's one kind of field to be in. It has the feature that if you figure something out, if you kind of are ahead of the pack, you figured something out, everybody knows that what you figured out is important. It has the downside that there are lots of other people chasing the same thing, and it's sort of a competitive area, and it's kind of lots of weird interpersonal things happen and so on. That's sort of plan A. Plan B is pick an area where it's like nobody's cared about that area for 100 years. And yet you can, you think it's interesting for some reason or another, and you can build a kind of tower in that area, and that tower is kind of unique. It's a thing. Now, maybe nobody cares about it. People might look at it and like, oh, okay, that's cool, and we don't care. For myself, I've tended to more do that second kind of thing. And, then you have to convince people that, yes, this is a tower that's worth climbing, that's worth looking at, and so on. But you kind of feel more unique, and you kind of have a different dynamic in terms of you're not part of a herd of people that are sort of all charging in the same direction. When I did particle physics, when I was a kid, I was sort of part of the herd charging in that direction. And I think I was, it's like, okay, I'm 17 years old or something, and I'm doing random particle physics stuff. And it's, at that point, I wasn't thinking particularly long-term about sort of how does this fit into some whole track of things that I want to do in my life. As years go by, and you start sort of building this tower, in my case of sort of a combination of basic science and technology, then eventually you realize, my gosh, I've spent 30 years on this, and it really matters which tower you built and whether you built the right tower and so on. But I think that that's a thing where sort of the strategy of what you do and kind of what you actually get into doing is important. Like, for example, I mean, right now in physics, it's this stuff that we've been able to do in the last couple of years is it's very surprising that it works as well as it does. But basically, we've sort of opened this door to, I suppose, what you have to call modern physics. I mean, modern physics has been devalued by the fact that, there's physics and then there's modern physics, and modern physics is what was discovered 100 years ago, or a little bit more than that. So I think we maybe what we've kind of been doing is kind of the next step from what was done like 100 years ago with the discovery of relativity and quantum mechanics and general relativity and so on. It's kind of the next major step of a different theoretical framework for physics. And I have to say, I'm super surprised at how well it's worked. And I'm also kind of pleased that there are all these approaches to mathematical physics that people have taken in intermediate years, many of which have been a bit untethered from anything where you can sort of say, this is how actual physics works. They're kind of, well, if you set up this and that and the other, we've got this elaborate piece of mathematical physics we can build. And they built those things, and they've often done rather elegant mathematics around them, but they've been rather untethered. And one of the things that I think is really cool, sort of from a, physics societal point of view or something, is that the things we figured out kind of provide a kind of an underlying machine code, an underlying foundation for lots of things that people have worked on and done really interesting things with in the intervening years. So they kind of plug into things that we've done and kind of give them a way to really, have a meaningful foundation. And that's pretty cool. So, I mean, for example, right now I can say, for people doing actual physics, is like, there's a lot of low-hanging fruit to be picked. You've got 5, maybe 10 years of runway there when the obvious low-hanging fruit will be picked. And I think, we can see perfectly well what that low-hanging fruit, some of what it's going to be. I mean, we have kind of a basic idea of how space and time and quantum mechanics and so on work, but somebody gets to actually discover the electron, for example. And that hasn't happened yet. Somebody, we now know how our stuff connects to things like causal set theory and spin networks and other kinds of mathematical physics. We don't yet know exactly how the connection to string theory works, although it's clear that there is one. And so that's, these are things where most of those are not particularly, one of the problems with the physics project, our physics project, is that, some things that one can do with it do not require a huge tower of knowledge of existing physics, and some do. There's quite a bit that can be studied kind of what I would now call Ruliologically, just studying it in terms of, these are simple rules, what do they do? There's this science, I wrote this whole big book called The New Kind of Science 20 years ago now, that was about kind of the science of simple programs and their consequences for modeling things in nature and so on. But that this kind of whole idea of you just set up some computational rule and you run it and you see what happens, there's a whole very basic kind of science, sort of a science underneath mathematics in some ways, that relates to that. And there's a lot that can be done in terms of understanding our sort of approach to physics that can be done at that kind of Ruliological level without, sort of the full quantum field theory stack, so to speak. But there's also a lot of stuff that needs kind of the knowledge of existing physics to really make progress. It'll be interesting to see who gets to discover the electron, so to speak. I mean, I think that and whether that needs, I suspect that's going to end up needing, and we're sort of building some of the apparatus that's needed. I suspect that needs a bunch of mathematical sophistication. I mean, essentially what we have to do, I mean, we're sort of backing into talking about how the physics project actually works. But one of the foundational ideas is, space is not just a background in which things are placed. It is a thing that has its own structure, and the structure it has is just a huge number of kind of atoms of space all connected by relations. And so in a sense, you have this giant graph or hypergraph that represents kind of all the points in space. They're not positioned anywhere particularly in space. All you know about them is this point has these relations to these other points. But when you have a sufficiently large number of these points and relations and so on, the limit of that ends up approximating the way that space and space-time work. And one of the things that then happens is, one of the things we don't know is why the universe is three-dimensional, as opposed to, or three dimensions of space, as opposed to 4, or as opposed to 2.6 dimensional. And so one of the things that happens in our models is that you have this kind of generalized notion of the structure of space as the limit of these graphs. And so calculus, for example, which is sort of studying continuum things, but you learn single variable calculus, you learn multivariate calculus, but you never learn calculus with a fractional number of variables because that's not been invented. And so
are you having to work on a generalization of that?
What's that?
Are you having to work on a generalization of calculus then?
Yeah. I mean, basically, one of the big things that we have to do, it's not yet done, is to generalize calculus to work when you have sort of fractional dimensional space and fractional numbers of variables. And, we know in outline how that works and in pieces of how that works. We know certain parts that we need in order to reproduce general relativity, the theory of gravity. But there is a mathematical structure that's needed there. And I suspect that sort of discovering the electron is going to require having a bunch of that mathematical structure in place. And we just, that's a thing where it's always, it's like this drive, the research by the results one wants, so to speak. It's a question of nobody ever really looked at this kind of, generalization of calculus because nobody ever needed it before. And if you say, is there existing mathematical work on this? Well, the answer is no. It's sort of a hole of something people haven't looked at. And it really helps. I mean, the fact that we're able to look at it reasonably coherently, what's critically helps is that we've done all kinds of computer simulations of this. We know basically how things work and how things have to work because we've seen it. And, I tend to have this kind of quote that I bring out with considerable regularity, which is, you're studying these simple rules. You might think that they would always have simple behavior. You might think, I'm much smarter than this simple rule. I'll be able to figure out what it does. But my sort of often wheeled out quote is, the computational animals are always smarter than we are. By which I mean that, you have this rule and you say, I'm sure it's going to do this, that, and the other. You actually run it, and by golly, it does something different. And it does something that you never guessed it could possibly do. Some bizarre thing that, we would have discovered, well, for example, in space-time, in our models, there are things like black holes, and there are also other bizarre kinds of structures, things I call space tunnels, for example, all kinds of weird things that, just found them by looking at the actual, what actually happens computationally. And I'm sure we haven't figured out what all of those kind of exotic things are, because sometimes you can't even recognize them in the structures you're building without having sort of some idea of what you're going to be able to see. But I think that an example. So, kind of our physics project, I would say, in terms of fundamental physics, is like a tremendous kind of it's a giant cascade of low-hanging fruit, so to speak. I mean, it amazes me what one's able to figure out. And the thing that is perhaps even the most remarkable is that the formalism that we've built for physics, I can talk a little bit about how that works, but the formalism we built for physics is something that turns out applies to a lot of other areas as well. And so the thing I've been doing the last few months actually is applying it to metamathematics and trying to use it will turn out that the fact that it's possible to do higher level mathematics, the fact that it's possible to talk about kind of mathematics abstractly rather than always going down to the level of individual axioms and moving symbols around and so on at the level of axioms. The fact that higher level mathematics is possible turns out to be the case for the same reason that we think that continuum space exists. That is that instead of, you could be kind of reduced in mathematics to studying things at the level of these symbols and axioms and so on. And then you would be sort of operating at the level of sort of the atoms of space. And the fact that there is a kind of a continuum limit of mathematics that is like the kind of higher level mathematics that people learn of sort of general theorems in mathematics and so on, that happens, it turns out, for the same reason that one has kind of this, that continuum space exists in physics. And that connection, it's sort of a bizarre connection that I didn't see coming at all, is something that comes out because sort of this formalism that we developed for the physics project also applies to, among other things, mathematics. And it turns out it also applies probably, well, I think it has a bunch of applications in biology and chemistry. In chemistry, the most exciting thing has to do with molecular computing and kind of thinking about, well, you know, when you study chemistry, you are told, you know, oh, we can compute, you know, the concentration of this or that molecule in you know, in this series of chemical reactions. I have to say that chemistry is one of those fields where I was like, when I learned it as a kid, I was like, I do not care about this. I will never, you know, this is totally uninteresting, et cetera, et cetera, et cetera. And I think I like to claim that that most of the chemistry I ever learnt, I learnt the night before some chemistry O-level exam when I was 14 or 15 or something. As it turns out, I've in subsequent years, well, partly because I've been interested in nanotechnology and also because in more recent years, because we built a big chemistry subsystem in Wolfram Language, and it's probably, for me, the best possible way to kind of learn a field deeply is to try and do computational language design around it, because that really is a very unforgiving process of do you really understand what's going on? And that's so now I probably know, I don't know elementary chemistry, but I do know the theory of chemistry, I think, decently well. You know, if you ask me about some specific, you know, reaction with copper sulfate or something, I would not have a clue. I mean, I'd probably type it into Wolfram Alpha and it would probably be able to do it for me. And it even has, we even now have step-by-step chemistry for chemistry students and so on. But I think the thing that, so, you know, one of the things then is that the usual view of chemistry is just you're looking at concentrations of molecules. One of the things that's come out of the physics project is a formalism where you can think about the sort of individual interactions of molecules. So molecule A interacts with B, interacts with C, and then that interacts back on A and so on. And you end up with these kind of causal graphs of interactions between molecules. And we don't know whether such things are important for molecular biology and other areas, but I suspect that they are. And I suspect it's sort of a big missing thing in molecular biology, for example, just as before one knew that DNA was a molecule that, you know, packed in billions of bits of information, one was like, oh, a molecule is just, you know, just knows what kind of molecule it is. And I think now my guess is that there's a huge amount of information in this kind of causal graph of interactions between molecules and so on. And that's something that sort of comes directly out of our physics project. And hopefully I get to explore that a bit in the next few months. But then it just turns out the formalism for the physics project looks to be applicable to all sorts of different areas. I don't know, maybe, you know, there's been a sort of mystery in biological evolution of having sort of a proper theory of natural selection that isn't the sort of more explanatory narrative story, but is something that is more formal. And perhaps that will come out of this as well. And there are a bunch of things in distributed computing that look really exciting and very near-term technological. There are a bunch of things about understanding economics, which may or may not work out. I think my test is, can we use these ideas to actually build a kind of new type of distributed blockchain that actually economically works? That's my kind of practical person's test for whether we understand something about economics. And actually, we had started, based on the physics project, this was an idea for how to build a kind of distributed blockchain. We started building that. And I realized, I just don't understand. You know, this thing is supposed to be a repository of value and has prices and things like that. And I realized I just do not understand how this works in economics or in this case. And so I realized we kind of have to have a theory of economics to understand what's going on. And I this is a case of probably 6 months ago now where I was like, I had some vague understanding of economics for a long time, but now I had kind of a very specific objective of understand, you know, things about sort of how economic systems work. And that caused me to try and sort of go along this path of understanding economics which if I was just like, I'm going to sit back and read economics textbooks, for me at least, they would kind of, the things I would look at what's on the page, I'd read the page. It's like, I don't know what's going on here particularly. I need some actual question that I'm trying to answer to drive that. But actually, one of the things that comes out of this is that this sort of formalism that came out of physics applies to all these other areas. We can take the successes of physics and the fact that physics is sort of the most advanced mathematical science and export those successes to these other areas. I mean, I might say that in terms of people learning physics, it's kind of a funny thing. If you look at my company, for example, we got a lot of physics PhDs and physics bachelor's degree people and people who've studied physics and so on. And probably more of that than people who've studied computer science. Certainly used to be the case. I don't know if that's still the case. And one of the things that I notice about physics is a remarkably successful export field. I mean, I would say the other ones that are runners up are, well, computer science is in some ways of teaching it, but not in the more traditional ways of teaching it, is a bit of an export field. Economics has actually been a bit of an export field. Philosophy has been a bit of an export field, although to different kinds of things. But physics is the top kind of quantitative export field. And there are many cases where, friends of mine who are CEOs of random companies and things will be like, have some problem they're trying to solve and so on. And I'll give them the advice, go hire some physicists. Even though, because why? I mean, I hope physics education continues to sort of stimulate this. It's kind of like, it's like you figure things out in a kind of structured, quantitative way, but you kind of expect that you'll get to the answer by all means necessary, so to speak. I mean, mathematics tends to be a bit more of a process. It matters the elegance and the process of what you're doing. Whereas in physics, there tends to be, at least at the more advanced research level, it's just like, let's just get to the answer by whatever means we need. And that means that physics, among academic subjects, often has the reputation that people will say, it's, physicists go into some area and people will say, the physicists are going to reinvent everything that's already been done in that area, which is often the case, but they often reinvent it better. And that's sort of a thing that goes on. But so I think, in terms of the things, I mean, I would say that in terms of things that are sort of low-hanging fruit accessible today, this whole area of Ruliology and studying simple programs and what they do and so on, that the fruits of that effort, the fruits of even rather, the things that I've done in that, have been very, very good in the sense that, a small amount of work in that area has led to models and sort of basic understanding of models that have been used in a huge number of different fields. And so it's a place where there's sort of a pivot point where you can, by doing sort of a small amount of work at this very foundational level, you can have effects that downstream are useful for lots of different fields. So this area of studying simple programs and what they do, it also has the feature that it's very accessible because it's a very young field, and the methods for studying it are, I've developed a bunch of them. Some other people have developed some, but they're not things where there's a huge tower of, you've got to learn hundreds of years of sort of intellectual technology, so to speak, to get to the point where you're doing research kinds of things in it. But I think and I think this thing that that's sort of, in a sense, that's the most basic science that you get to from sort of computation. I would say the other big thing, which is more general than physics, is kind of computational X, where X can be any field you can name, so to speak, is the future of pretty much everything. I mean, this is, there was a time 300 years ago or so now when mathematical X was the thing that looked to be kind of the future of everything. And a lot of fields got mathematicized. Physics got mathematicized. It hadn't been mathematicized before, Newton and Galileo and people like that. It got mathematicized in the late 1600s, early 1700s. And then people thought, oh, engineering got mathematicized as a result of that. People thought in the beginning of the 1800s, people thought there would be a social physics, which would kind of mathematicize economics, or what was then emerging as economics and all these other fields. That didn't quite so much happen. And people even imagined there might be a mathematical biology that would mathematicize biology. That didn't happen in a serious way. But what we now see is that there's computational X, and that really is happening across sort of all X, because computation is a much more general paradigm than mathematics, and it's something that can be sort of applied across all these areas. And I think the thing that, a lot of my life work has been devoted to building this computational language, Wolfram language, which kind of is a way of expressing sort of computational thoughts in a way that both humans can understand and computers can understand. And it's kind of one of the things that's leading to is letting people sort of get to computational X without learning how to write for loops in a computer science class. Because the fact is, computer science education is kind of weird, because it's sort of partly, it's deeply anchored, the sort of what is possible to do with computers is very great. And computer science education is a little bit like, learning some aspects of it, a little bit like learning the alchemical foundations of sort of modern physical science or something. It's kind of like, yes, you could learn how to write some loop that causes the registers to get updated in the ALU of the computer, but we don't need to operate at that level as humans, so to speak. I mean, a small number of humans need to operate at that level to design computers, just as a small number of humans operate at the level of, designing car engines and so on. But most people just get to drive their cars around without knowing how the engine works, so to speak. And I think when it comes to sort of computational X, the thing that is sort of the main thing achieved by the computational language we've built is that you can get to sort of thinking about things computationally without going through those sort of low-level steps. And so, I would say that for people entering kind of the world of kind of intellectual sorts of things these days, computational X, for some X, is a very, very, very good bet. And some X's, it's been reasonably well developed already. For some values of X, so to speak, there's pretty much nothing done. And you can go look at type a search on the web, computational, whatever. And if you find almost nothing there, that's probably a pretty good bet for a future field. And what tends to happen, it's always fun. I've watched enough fields grow up in my time that there'll be an early set of people that get into the field. And then decades will go by. And then it'll be like, there'll be some picture of the early people in the field, and it'll be like the founders of field X or something. And usually some of those people are young at the time. Some of them aren't so young. People, I think, one doesn't get to pick the time in history at which one lives, so to speak. But at any given time in history, there are certain sort of doors that are being opened. And, one might be not so young, and the door that is really relevant to, that really fits in with one's way of thinking about things suddenly, finally opens, and one's able to pursue that area. And so you typically see kind of a mixture in new fields. You typically see a mixture of young people and not so young people who kind of enter these things. And it's always remarkable that, people who get into these things early, the rising tide, raises all boats, so to speak. And those people typically, if they stick with it, become sort of the distinguished people in the field X number of decades later. So it's but I think, people somehow, people have the point of view, you have to, the thing I should say is that sort of one of the subtexts to all of this is, research is a thing that people can do. Not everybody who studies physics and does well studying physics is going to be good at doing research. In fact, there are plenty of people who will study some field and mathematics, physics, do really well in competitions, whatever else, and they're actually quite unsuitable for research. They are great at doing things that don't involve kind of the unknown, going off into the unknown. I'm reminded of a chap who worked at my company for many years, I just got a physics PhD and came and said, look, I just don't do research very well. It turned out to be a person who's a fantastic, really outstanding figure out, you could give them a very big problem, like, solve the problem of doing natural language understanding for a large chunk of Wolfram alpha, and he could go off and solve that problem. But it's like, somebody else has to say what problem should be solved, so to speak. And different, different people, work differently in that regard. And I think, in fact, I should give a shout out for one thing that I've been involved in the last 20 years or so, which is it's like, how do you teach people to do that stuff? We have a summer school for grown-ups and a summer camp for high school students every year that we've been doing for, well, the summer school for 20 years, the summer camp for maybe 11 years now. I think we actually just added a piece for middle school kids as well. But I'm sorry, I don't know how that. I haven't lived in England so long that I don't know how that quite translates into high school. I guess is age 14 to 18.
Yeah, I think they're all encompassed within secondary school here, but right. The system's a bit weird. Yeah,
right. It changed when I was a kid. It changed from, but in any case, the it's actually perhaps interesting for people to see if you go on the web and you find our summer school and summer camp. You can find all the projects people have done in these past years, and it's sort of an interesting process because it's, the summer school is 3 weeks, the summer camp is 2 weeks, and it's like, can people do a research type project in that period of time? And the thing I found is, well, given the tools that we've built, that's one critical piece, and then given a decent selection of a project, and I end up seeming to be the person who eventually figures out all of the projects, so to speak. It's my, I haven't been a professor or teacher type for what is it, 35 years now. And this is those few weeks are my moments of sort of extreme professoring or something mostly consists of invent 150 projects or something that are suitable for people to do. And it's very satisfying because some of the ones that I sort of invented 20 years ago have turned into whole career-long stories for people, which is really neat. But in any case, let's see. So what else would you like to ask about? You've gotten me chatting about all kinds of.
Going back to the models, I find interesting. We could talk about the physics model in a sec, but applying that to other areas. So say like if a model for economics was causally invariant in the same way, would you get things like special relativity of economics like cropping up? Do those sort of things transfer?
Yep, I think so. I don't know what it is yet. I've been wondering about that. I mean, I think it's a question of I had kind of a possible way of thinking about that, which is, what is the key ideas of special relativity in the end have to do with things like time dilation. And so first of all, you have to have an idea of motion, and that's not a completely trivial thing. But in a sense, in our kind of computational view of how the universe works, you can either spend your computational effort sort of figuring out how you're going to evolve in time, how you're going to progress in time, or you can use your computational effort seeing how you kind of get repositioned somewhere in space. And so in a sense, if you're moving in space, you're using up your computational budget on your motion, and you don't have as much computational budget to evolve in time. And that's kind of the foundational cause of time dilation, because time effectively runs more slowly because you're using the computational resources you have to do your motion, so to speak. And so, I have wondered whether there's an analog of that in economics, and I've been trying to figure out, like, for example, if you imagine some agricultural society where people are growing lettuces or something, and you can either sort of sell your lettuce locally, or you have to kind of translate your lettuce to another place. You're kind of using up some resources, sort of moving your lettuce from here to there, and that's kind of and so that's sort of that is potentially a rough kind of price-based analog of time dilation. Maybe it's a thought about how that might work. But yes, the thing that I think my current guess is that in economics, for example, what is the lowest level of economics? Well, it's people doing transactions with each other. and there's this giant network of transactions people are doing with each other. What is not obvious is that from that network of transactions, there emerge things like global prices. It could be the case that everything is just a barter transaction, and there's no meaningful notion of money, for example, where there is a sort of a fixed price, a value for things that is in some sense global. And my guess is that the reason that arises is for the same kind of reason that we have a global notion of space, and that essentially it's always difficult to talk about things one hasn't figured out. My current thinking is that the analog of space and general relativity and so on will end up being the existence of a price, the existence of some kind of somewhat global price, will be the analog of the existence of a global reference frame in space, where one can imagine that there is things happening all across space at a certain moment in time, that's a reasonable thing to think about doing, which it might not be. That can be the thing one thinks about, I think is kind of, I'm guessing is kind of the analog of the idea that one can have a global price for something. But I'm not sure yet. I mean, that's a thing yet to be figured out. It's a thing, I'd love to see it figured out.
It's fascinating.
It's fun to think about, but it's one of these things where if somebody else could figure it out, it'd be great. I think one of the things that we've been doing in this physics project is I've been doing it as a very open science project. So, we live stream our sort of working sessions, and we post every, I've even been recording, I think it's probably the most boring video you can imagine watching, but I've been doing these video work logs where I'm just working on my own, working on these projects and things. I just record, I screen record, and hours and hours, 6 hours of stuff, and I haven't looked at them again, but we post them on the web. And part of the thing that's interesting about that, actually, which I think people have made use of, is when you read a thing that I've written or something about our physics project, every picture in there, you can click it. It's got Wolfram Language code that actually runs. That's been a very important thing, like at our summer schools and winter schools and so on. People just take that code and start from that point and start figuring out new things from that. But also, people sort of wondered, well, how did this, what were you doing? Where did this sentence come from in this thing you've written? Well, you can actually go back and find the video where that sentence got typed in, so to speak. And that way, you kind of know, well, maybe I made a mistake, who knows? But maybe there was some whole big thing. I mean, sometimes it can be the case in things I write, at least, that it ends up in one sentence, but actually it was 3 hours of figuring out some elaborate thing with a bunch of computations and so on, and then the result is, and it works this way. And and I don't really think it's important, because I think it's semi-obvious that it works that way. I don't think it's important to show kind of the 3 hours of figuring out that it was obvious that it worked that way, so to speak. But that's sort of this kind of approach to open science gives one the opportunity to do that. So I think let's see, what were you asking? You were asking about other. Well, yeah, I mean the sort of the story of what. Okay, so there's a very surprising thing, which sort of I got backed into from the physics project. So in the physics project, we're imagining there is some rule that determines the sort of updating of this network that represents space and everything in space in the universe. And this rule updates the thing, and it leads to there are different possible update sequences that can happen, and those correspond to the different possible histories in quantum mechanics and so on. But the question that still leaves open is, okay, why is the universe following this rule and not another rule? And so thinking about that question then arises, well, we say you're using this rule, but you're applying it in all possible ways. Why don't you just imagine that you're using all possible rules? And so imagine that essentially you've got this thing where you're running all possible computations in all possible ways. And that thing, which turns out has never been studied before, is a thing I now call the Ruliad. And a lot of people say, that's kind of an obvious object. It's kind of surprising nobody has ever looked at that before. But it's this thing where you're sort of running all possible computations with all possible initial conditions for an infinite time. And that's a thing. It's a sort of a necessary formal thing that exists. Well, now the issue is we are observers somehow embedded in that thing, observing that thing. And it turns out that if we imagine certain features of us, like we imagine we're computationally bounded, we imagine that we at least believe that we have some persistence through time, with those two constraints, that leads us to take samples of this Ruliad that have effective laws that we perceive that correspond to major laws of physics. And so that's, so in a sense, it's a very bizarre thing, because from this kind of necessary sort of formal underlying structure, the way that we are sort of observing that inevitably ends us up with general relativity and quantum mechanics. But so these things sort of emerge from this kind of necessary object. And it then turns out that mathematics also emerges from that object. And so in a sense, when we do physics, we are sampling the Ruliad as physical observers. When we do mathematics, we're sampling the Ruliad as mathematical observers who have slightly different characteristics. And that's kind of a way of understanding sort of what it means, what mathematics is, and a way to understand that. And so when we think about things like, I don't know, molecular computing or chemistry or molecular biology, what we're in a sense doing is, we might think about it in terms of the Ruliad. We don't have to probably go that far down in the sort of hierarchy of ideas, but essentially the big question is, we've got all these processes going on. What is the chemical observer or the biological observer? What are they like? And so one of the things I've been interested in recently is, I mentioned this kind of causal graphs of molecular interactions, but there's sort of the question of, is it just the concentration of, I don't know, hormone X or something that causes this thing to happen? Or is it the binding of that thing to some membrane that actually looks at individual molecules and says, oh, did this molecule go into this pore in this membrane before that one did, and ask things which are beyond the level of what traditional chemistry with chemical concentrations would ask. And so, for example, one of the questions is, can one sort of invent a device that is like a measuring device that is kind of like a molecular biology style chemical observer? What is that like? Just as, one of the things that I'm interested in right now is a proto thing, which doesn't really exist yet, that I'm calling observer theory, which is kind of the theory of how it is that what kinds of samplings of this Ruliad can actually be done. And so that leads one to a project that I have coming up. Actually, I haven't done it yet, so can't really comment on it too much, is to just understand, how do you measure things? And I do know that, like in Wolfram Alpha, we have sort of the world's largest collection of units and so on. And so there are 10,000 kinds of units for things, including very exotic ones, like one of my favorite exotics is moles per acre, which you might think was, you put fertilizer on a field and it's, the amount of fertilizer you put down. Turns out it's actual moles, like the little critters. But it's the amount of, it measures the aeration of soil and so on. But anyway, there are lots of exotic things like that. But the question is, when you are measuring those kinds of things, sort of one of the things I've been interested in is, can you make a kind of universal measuring device where it measures only, has a camera and it has a chemical sensor, broad spectrum chemical sensor, has various other kinds of things, and you deduce all these other kinds of measured quantities. But more than that, sort of what is the concept? How does measurement really work? That is, in our, I don't know, something like, our eyes, photons come in and they produce electrical signals on our retina, and they do, they have various kinds of amplification happen and so on. But what is sort of, like when Turing machines were invented as a model of computation in 1936, Alan Turing kind of had in mind the way that sort of humans compute things, and the way that bank clerks go and, take information and put it in file cabinets. Well, they did in those days, at least. And so the question is, what's sort of the analog of that for measurement? What's the kind of the analog of a Turing machine for the observer for measurement? And that's
a universal Turing machine. Yeah.
What's that?
And a universal Turing machine sort of measurement.
Yeah, well, right. I mean, the question is, what's the thing that you could potentially have a universal measuring device, and sort of how does that work, and what is the concept of universality in that case? Is a little different than a Turing machine, where it's like feed an input, crunch, 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 generate output. This is a different thing. It's a different kind of workflow of what you're trying to achieve. Of there's a thing happening in the world, and you're kind of turning it into a something that is somehow relevant to the observer. I don't know how it works yet. So again, I'm trying to describe something I don't understand yet. So it's which is always.
Does taking different sort of measurements sort of correspond to moving through Ruliad space in any way? Are they equivalent?
Possibly. I mean, I think that yes, I think that different positions in Ruliad space correspond to different ways to parse the universe, so to speak.
Okay.
And yes, different kinds of approaches to measurement probably can be parameterized that way. I mean, kind of the assumption is that just as sort of different humans have a different way of understanding the world because their brains have been learnt different things and are constructed in different ways, it's kind of like that's a small distance in Ruliad space to get to the putative aliens, the extraterrestrial alien, whatever. That's potentially much further in Ruliad space, sufficiently far that we don't have any hope of sort of understanding that from where we are right now, probably. And it's kind of like you're a certain distance apart in physical space, you're a certain distance apart in Ruliad space. And what is the way of thinking about those things which are separated in Ruliad space? And that it's, for me, that's kind of, yes, that's sort of inventing different frameworks for thinking about things, inventing different kinds of things you can measure. By the way, I mean, it's, when you have molecules in a gas, what do you measure? You measure pressure, you measure velocity, you measure temperature. But you might also be measuring that weird little correlation between, this little triple of molecules that does this and this and this, which for us right now, with our approaches to measurement and our way of doing physics right now, it's like, we don't care about that. All we care about is pressure and temperature and the things that you learn about in gas laws and so on. And that's that's the part that you kind of need a different conceptual frame of science. One thing that happens is pure tool building that moves things forward. You get to have a telescope, you get to have a microscope, you get to have a computer. Those are tool type things that allow you to methodologically move forward. The other big thing that happens is kind of new ways of thinking about things. Computation is both a tooling kind of story and a new way of thinking about things kind of story. I think most people still are in the belief that it's only a tooling kind of story. It's not. It's also a way of thinking about things kind of story. And that's only kind of in its early years, I would say, of developing. But that's so when it comes to how do we move around in Ruliad space, part of the story is we need sort of a different conceptual framework for thinking about things. I mean, the things I've done, this whole idea of looking at simple programs and what they do, people could have done that 2,000 years ago. There's really nothing that stops one from imagining, make a mosaic of my Rule 30 cellular automata. You just follow these rules, et cetera, et cetera, et cetera. Probably nobody did it. Probably if somebody had done it, science would have evolved in a rather different way. But why did nobody do it? Well, nobody did it because there was no conceptual framework in which would say that would be in any way interesting. And and sometimes the conceptual framework can develop only after you have lots of examples and tools and all this kind of thing. And the thing that's happened with the physics project is something which I'm sort of realizing is a conceptual framework, I'm sort of referring to it as a kind of fourth paradigm for thinking about science and modeling in science. And it's kind of like, the first paradigm was what was done in antiquity, where people sort of just said, what are things made of? Are things made of atoms? Are things made of this? Are things made of that? And that was something where you didn't really have much of a notion of dynamic progress or time. It was just what are things made of? And there are many fields of science where we're still basically in the what are things made of stage, so to speak, the kind of structural stage. Well, then move forward in time to the 1600s, and you get the mathematicization of science, and the idea that mathematical equations can describe things in the world, and then, for example, time just becomes a parameter in the equations. It's just you're solving a differential equation. It has a time variable. You can pick the value of that time variable. You know what the system does. Then you move forward to basically the 1980s, and you get to sort of the computation paradigm, where instead of saying let's put have a mathematical equation, you say let's have a simple program, and to know what a system is going to do, let's run the program and see what it does. One of the important phenomena there is this thing I call computational irreducibility, that to find out what the program is going to do, you basically don't have much choice but to just run the program and see what happens. And that's so there's a notion of time that's sort of this inexorable progressive computation. And that's sort of a feature of this kind of third paradigm for thinking about models in science, is this kind of computational paradigm where you're sort of writing down rules and then seeing what happens. Well, then it's the sort of fourth paradigm, which is the thing that's come out of the physics project, is this idea there are many different paths. There are many different things that can happen, many different threads of time that branch and merge and so on. And in order to even be able to say what happened, you need an observer who is parsing out all those different threads of time. And so that's kind of the that's sort of this fourth paradigm for thinking about science, and it's one which looks to be really fertile. And we're only at probably 6 months into thinking about what the implications of that are, and it's kind of very very early days for that. I'm noticing that the time, talking of the progression of time, we're yeah, heading to other things that I have to do. So if let's make sure we cover if there are particular things you wanted to ask about.
That's right. How long do you think you have, just to estimate?
Maximum about 15 minutes.
Okay, so, sure.
Well, I mean, I believe. Let me just check my. Let me check. Yes, that would be a correct estimate.
Okay. Cool. Well, I think one of the things that would be cool to talk about, one of the things that I found most beautiful and striking whilst reading the book that you wrote on the physics project, is that both quantum mechanics and relativity are kind of the same thing. So I think that would be really cool to talk about. If you could explain that for the audience, that would be. Let
me see if I can. In
a brief amount of time, yeah.
You've got to start off by thinking about sort of the basic stuff of the universe is this giant network that represents space and everything in space. So just like, in a fluid or something, there's a bunch of molecules down there, but there are sort of things you can make out of the fluid, like a vortex or something. That's kind of how we imagine the things that we know about in the universe, like electrons and so on, what they are. And then there's kind of for us, this kind of this network is continually getting rewritten. So there's rules that say if there's a piece of network that looks like this, turn it into one that looks like that. That's kind of the progress of time, is the progressive rewriting of this network. And there's sort of a question of what does the network look like on average after it's run for a while? And the answer is, much like molecular dynamics limits to fluid mechanics, the dynamics of these networks limits to general relativity, the standard theory of gravity from 1915. One feature of, one thing in general relativity is general relativity starts talking about what are straight lines like? If we just have a flat space, a flat piece of paper, or whatever, we want to know what's the shortest distance between 2 points. It's a straight line. And but if we have a curved space, the shortest distance between 2 points is now a curved line, just like on the surface of the Earth, it's a great circle, for example. And in general relativity, the big idea is that energy and mass deform space so that the shortest distance between 2 points is no longer a straight line, but something curved. And that deformation is associated with gravity. So the presence of energy or mass deforms the structure of space, curves space, which means that straight lines are now no longer straight, they're deflected. And that deflection corresponds to what we interpret as the force of gravity. So In our models, the same thing happens. What is energy in our models? Energy, I was amazed that it was as simple as this. Energy is basically the density of activity in the network, the number of rewrites that are happening per unit volume, essentially. It's a little trickier than that because the space itself, the system itself is defining the notion of volume, so it ends up being the flux of causal edges through space-like hypersurfaces is a slightly more formal definition of energy density in our models. But okay, so energy density in this network that is space corresponds to corresponds to the sort of rate of rewrites, and we ask then, how does that deform the emergent space that we get from these networks? And the answer is, it does it in exactly the same way that general relativity says it should do it, and the presence of energy, momentum, mass associated with activity in the network will make the network behave like a curved space and deform GD6, shortest paths in the network. Okay, so now how does quantum mechanics work? Well, the big thing in our models is there are all these possible rewrites that can occur. There are many possible paths of rewrites. And quantum mechanics, that's exactly what it sort of talks about. Classical mechanics is about sort of definite things happen in the world. Quantum mechanics is about there are many possible paths of things that can happen, and we kind of get to see the probabilities of things based on the aggregate of all those paths. So in our systems, we have these things we call multi-way graphs, which represent all possible histories. And so quantum mechanics is kind of the aggregate effect of all those possible histories, and things like quantum. So when we look at this kind of multi-way graph, it's branching, it's merging, so on, we can imagine just sort of slicing across, and it's doing that through time. We can imagine slicing through it at a fixed time, so to speak. We make reference frames much like we do in relativity, but that's kind of more of a detail. But basically, we're saying at a fixed time, slice through this multi-way graph. What do you have? You have a bunch of sort of threads of history that are poking through that surface that you slice through. So you have all these threads of history. Those correspond to different, essentially, quantum states of the system. And you have this space that is kind of the layout of all those different threads of history. And you can kind of say two threads of history are nearby if they have a common ancestor. So then this space of all these threads of history we talk about as branchial space, the space of quantum branches. And branchial space has a structure, just like physical space has a structure. What is the interpretation in physical space? You know, we move around, we know kind of what motion is in physical space. What's the analog in branchial space? It seems to be the case that the analog in branchial space is the phase of a quantum amplitude. So quantum amplitudes in standard quantum mechanics are complex numbers, and there's some the phase, what angle you're at in the complex plane is one part of that complex number, and we think that position in branchial space, or difference between positions, distance in branchial space, is basically quantum phase. So then what one's thinking about is one's got a GD6, a shortest path through this multi-way graph, and it then turns out that energy momentum in the multi-way graph, which is also activity in the system, deflects GD6 in this multi-way path. Well, what is the effect of deflecting a GD6? The effect is to move, which, just like, you know, when a spacecraft goes past a planet or something, it's deflected by the gravity of the planet. So similarly, this quantum history is deflected in this branchial space by the presence of energy momentum. And so what is deflection in branchial space? Well, it is a change of phase of the quantum amplitude. And it then turns out that sort of the core of quantum mechanics, not how it's taught at the lowest levels these days yet, but sort of the way people understand it ultimately, is a thing invented by a physicist I knew pretty well, named Richard Feynman, a thing called the Feynman path integral, which is a way of interpreting quantum mechanics in terms of looking at kind of the evolution of phases of possible quantum histories. And it turns out that it looks as if the kind of the Feynman path integral is associated with the deflection of paths in branchial space associated with energy momentum. And the Feynman path integral, the formula is the quantum phase is e to the I square root of minus 1 times a thing called the action divided by h bar, Planck's constant over 2 pi. And the action is essentially a relativistically invariant version of energy density. So what we're seeing is the kind of what is deflection in physical space associated with energy becomes deflection in Branchial space in the kind of quantum side of things. And that means that that phenomenon that leads to Einstein's equations in physical space is the exact same thing that leads to the Feynman path integral, which is the thing that leads to quantum mechanics in Branchial space. So it turns out that basically general relativity and quantum mechanics are the same theory, but just played out in different kinds of space. It's a big shame that Dick Feynman isn't still alive. He would have really.
I find that really cool.
I talked to him for a long, long time about where does what he thought was the formula in quantum mechanics is sort of for time evolution is e to the IHT, where h is the Hamiltonian or the energy function, t is time. And in thermodynamics, the sort of key formula is e to the minus beta h, where beta is the inverse temperature and h is again the energy function. And I spent ages talking to him about why are these the same? Why do they both have the same exponential form? One is in imaginary time, one is, how are they related? And I think we now actually know the answer. So that's cool. Although there's a certain depth of mathematics you need. I mean, the e to the minus beta h comes from statistical mechanics, which is yet another story of how that's all connected in.
Well, you don't have time to get
turns out,
yeah.
Right. It's But anyway, so that was a super fast rendition of why quantum mechanics and general relativity are the same theory, so to speak. I mean, that has had resonances in lots of things people have looked at, like the holographic principle, the correspondence between anti-de Sitter space and conformal field theory. That is frankly, I think a much more obscure way of discussing these kinds of things. But that's been a popular thing, and it's come out of string theory and so on. That appears to be basically to do with the correspondence between physical space and Branchial space. And there's this thing we call the multi-way causal graph, which kind of encompasses both of those things, and essentially there's projections in one direction or the other, and so on. But that's kind of the story of how this is working. I think that the good news is, in a sense, that although the things that come up in our physics project, there's an increasingly large tower of sort of technical ideas that are involved, and they're perhaps, fortunately, unfortunately, they're not just ideas from physics. They're also ideas from kind of the upper reaches of pure mathematics, and also from the upper reaches of theoretical computer science. And those all kind of get mixed together. But I think it's still the case, climb the tower quickly because the tower is getting higher, so to speak. I mean, in other words, I think our physics project is still, it's possible to learn a large fraction of what is known in it. It's plausible to do that. I think it will not be plausible, and I know there will come a point where people are doing all kinds of things with it that I don't understand at all. And there's some directions where that's already happening, but when fields get bigger, it gets harder and harder to kind of understand the whole thing. But now it's still possible, I think.
Okay. So on that note, I'm taking it that's the time you have done.
Yes, I pretty much. I have to disappear in a moment here.
Also,
otherwise, I don't get to eat any lunch before the next thing that I have.
Oh God, yeah, I can't do that. But thank you for spending so much of your valuable time with me.
It was fun. It was good. Lots of fun things. I think we talked about lots of interesting stuff. All right. Well, good luck with your trajectory in college, university, I guess. Uni. Is it really called uni in British English these days?
Uni. Yeah, uni.
Fascinating. That wasn't a term 40 years ago, 45 years ago. I lived in England.
Americanized language, I guess. Yeah.
No, that's not American. That's absolutely not American. That would be Australian and things like that. Not American. In American, the sole name for that thing is college.
Oh, okay. They don't use the word uni at all.
Nope.
Okay.
Anyway, well, nice to chat.
Yeah.
And, thanks so much.
No, it's amazing to meet you. So, extraordinarily impressive, isn't he? I hope that's inspired you to find out more about his work. Personally, I hope that one day I'll have the chance to interview Stephen Wolfram again, as there are still so many questions I'd like to ask. Thanks for tuning in and for your continued support. Please like, share, comment, and subscribe. Until then, looking forward to the next interview.